So for this example, we are going to look at the idea of independence with some conditional probabilities in this story problem. Now, it's important that we are going to define the probabilities in parts A, B, and C, and then kind of do some extra things with them in parts D through G. So, what is the probability that someone gets cancer? Well, let's go back and take a look at the previous paragraph. Prostate cancer for men and breast cancer for women have roughly a 1 in 7 or 14.3% chance of affecting those who live until their 90s. For those who have cancer, the test will only show negative 2% of the time. Suppose the current test for cancer rate is 85% negative. So what are the chances that somebody will get this cancer? So to do so, well, we can just look at the first statement of the story problem. The first statement of the story problem explains that the chances of getting breast cancer is 1 in 7. So probability of cancer is 0.143%. Or sorry, 14.3% or 0.143. Now, for these problems, I'm going to keep them in decimal because if we have to multiplying the percentages are going to give us different answers than the decimals. So we're going to keep them in decimal form. Now it says, what is the probability that they test negative? Well, the probability of just testing negative is just 85% or 0.85. Now, given they have cancer, what is the chance of testing negative? Well, luckily, this is a very low failure rate if they have cancer and they test negative. So this is choosing from the pool of those who have cancer. What are the chances that they show up negative? The good news is it's only 2% or 0.02. And the reason why that's good is because the cancer test is 98% effective. So, what is the probability of getting cancer and testing negative? Now, there's a subtle distinction here. The probability of getting cancer is PC. That's the probability of getting cancer. And testing negative. So this is a separate event. The probability of testing negative would be N, choose C. Now, the reason why we have this is because you are getting cancer and testing negative while getting the cancer. So that's why we did not go P of C times P of N. This is P of C times P of N having chosen C here. So if we hadn't done P of C first, then we wouldn't be multiplying by this. So therefore, we have 0.143 times 0.02, which gives us 0.0029 or 0.29%. Now, here's a fun one. What is the probability of getting cancer or testing negative? Now, getting cancer is P of C. Testing negative, now notice this is an OR. The OR means that we would add the P of N. But is there an overlap between getting cancer and testing negative? Because remember in the previous video, if we have an overlap or non-mutually exclusive events, we have to subtract the overlap. Well, here's our overlap, P of C and N. So this means what we found in part D of getting cancer and testing negative. So what I'm going to highlight in yellow, getting cancer and testing negative, is this right here. So if we were to look at the probability of getting cancer, that would be the 0.143. testing negative is 0.85. Then we're going to subtract, this is what we found over here, 0.0029, and we get an answer of 0.9901 or 99.01%. So this is the probability of getting cancer or testing negative. It's pretty high because testing negative is pretty high, so it's 85 already. And then we throw in the 14%, but we have to eliminate that overlap. Now it says, are having cancer and testing negative mutually exclusive? And the answer is no. Definitely not. They are definitely not mutually exclusive. You can test negative and have cancer. And this is because you can test negative and have cancer. And we saw that with the probability of testing negative and having cancer. That exists. That's not zero. Are having cancer and testing negative independent? And absolutely not. You are not having independence here with testing cancer or having cancer and testing negative for many reasons. And I want to show you the mathematical reason why you can't do it. Because it says that if you, like, all of these have to be true for mathematical independence. So if you have, probability of C having chosen N, well, that would have to be equal to the probability of C. The probability of N having chosen C has to be equal to the probability of N. And the probability of C and N has to be the same as the probability of C times the probability of N. But here's the thing. We've seen what the probability of N choose C has been, because the probability of testing negative if you have cancer is 0.02, and the probability of testing negative is 0.85. And since these are not the same thing, since the probability of this is not the same as the probability of this, these are not independent events. Having cancer and choosing and getting a negative is not the same as just getting a negative without the cancer. So these are definitely not independent by a long shot. You could explain that without the mathematics, but it's kind of nice to tie in this mathematical definition to that. Well, thank you very much for getting through a long session 5. And session 6, which is going to be talking about the tail end of this probability, is going to be a lot shorter, which is going to be nice. But I appreciate the hard work, and I will see you at the back end of this video.